Hi, this is the first video I'm going to teach you in this semester, and is about infinite series and sequences. There is 2 points, and there are 2 points you will get after finishing this section. You will get uh, the first one. You may sum infinitely many numbers. Okay, of course, under some circumstances, and the second ability you will get after finishing this section, and you may express any function. Say trigonometric logarithmic, say hyperbolic, and so you may express any function in terms of a polynomial of infinitely many terms. Okay, those are, you will get some abilities. Of course, this is also some conditions, under some conditions. Okay, as I said at the beginning, we are going to talk about infinite series and sequences. Okay, let's introduce infinite sequences. A function whose domain is the natural number is called an infinite sequence. Okay. A remark. We will be interested in only infinite sequences, and that is why we abbreviate these sequences. Yes. So, afterwards, by sequences, we will understand an infinite sequences. So, okay, an example. Let's write here a function whose domain natural numbers as from the natural number to real numbers, or you can write here a complex numbers or rational numbers. If your range is real numbers, then you say that this is a real sequences. Similarly, complex sequences, rational sequences. But afterwards, we will be interested in only real number sequences. Okay. And our domain is natural number. Then we have S1, S2, S of 3, S of n, and so on. Okay. We call this is the first term. Similarly, second term. Third term. Okay, sorry. Third term. And this one, we say it general term. This is a bit deserve interest, because the general term is explain us how to a sequence is defined. I mean, let's write here S of n 1 over n. This one is the general term. Indeed, there is no difference between sequences with the numbers. Of course, from the point of the definition of function. Because let's write here f of x equals to 1 of x. But at the right hand side, we may understand x may take the value, for example, -1. But at the left hand side, we understand only n can take the values from the natural number. So let's move this part. Okay. And the terms of these sequences, 1, 1 over 2, 1 over 3, and so on. Okay. So afterwards, we show a sequence as subscript n. By the way, we show the first term S1, second term S2, S3, Sn, and 1, 2, 3, n are called indexes of this sequence. Okay. Index of sequence. As I said before, by a sequence, we mean a function. So, under the condition that the domain of this function is natural number. Okay. So, we will be interested of this function by the limit properties. But let me write here a remark. We will be interested in infinite limits of sequences. And from the first semester of this course, we know how to calculate infinite limits of a function. So here is same. Nothing difference. Let me give some examples. Okay, Sn 1 over n. Sn n over n plus 1 n squared plus n over n minus 1. And as in this remark, we are interested in only the infinite limits. So that's why. For example, if I would ask to you how to calculate this limit. I'm pretty sure that you will answer okay like this. In this way you will answer. And in case sequences, the method is same. I mean, okay, Sn is a function, so let's write here Sn equals to 1 over infinity 0. This means that Sn, this means that 1 over 2, 1 over 3, 1 over n, and so. If your limit of a sequence is a real number, then your sequences is called convergence. Otherwise, for instance, if we had found this limit is an infinity, positive or negative infinity, then we will say that this limit is called divergence. Divergent, yes. Okay. Now I'm going to say something which is not correct from the mathematical perspective, but we may write here S1, S2, S3, Sn, and here the term in the infinity order. Let's write here as infinity. This one is 0. If this one is not a real number, for instance, here is positive or negative infinity, then we have no limits. Then we call such a sequence is divergent. Okay, but this is not correct from the mathematical perspective. So in order to be understandable, I wrote here like that. Just a moment. Okay, let's make you some definition. A convergent are respectively divergent sequence is a sequence such that the limit, of course infinite limit, the infinite limit exists. In divergent case, no exist. Okay. So let's continue the examples. Okay. This one for the sequences, of course the limit, this is a rational function. I mean a polynomial is divided by another polynomial, so this limit is related to the degrees of these polynomials, and the degrees of these polynomials are equal, so that's why the leading coefficients decide the limits. Then the leading coefficients 1 1, then it means that limit this sequence equals to 1, and this one is 0. Let's look here, infinite limits. This is again a rational function, but the denominator's degree is 1, so that's why, and the other one is 2, that's why this limit should be infinity. Okay, so we can say that divergent, convergent, and so. Okay, that is the last thing I'm going to say about the sequences. This notion is familiar to you from the first semester. Let me write here and you will understand. Okay. Monotone increasing or decreasing. Okay. You know this notion already to calculate an extreme points for function, and you will remember when I will give this definition. Okay, let Sn be a sequences. So it's called uh, monotone increasing if n smaller than, let's write here I for indices and I plus 1, while this inequality satisfies. So just a moment. Okay, when we have this inequality, so this one is satisfied, then this is monotone increasing, otherwise monotone decreasing if n smaller than n plus 1, Sn greater than Sn plus 1, then is called monotone decreasing. Yes, you know already this notion from the first semester. Okay, this is all for sequences and enough. Let's start series. Okay, which is much more longer than sequences. Okay, by giving its definition, we can start. Okay, until now we have shown that a sequence is by the letter S, and from now we will show a sequences by letter A, namely let A, K be a sequences. It doesn't matter what you choose, this letter or this one. You can write here N, P, I, J, it doesn't matter. And the same is true for S or A. This is not important. Okay. The sum A1, A2, A3 is called series. Yes, And we may show a series by using the sum symbol, I mean the sigma. So this one equals to k from 1 to infinity ak. Okay, this is the definition of a series, and a series is the sum of the terms of a sequences. Of course, a series involves infinitely many elements. So it's called infinite series, but for abbreviation, we hereinafter we call just series, not necessarily the word infinite. Okay. Example. We are already familiar with the sequence. AK 1 over k. Elements 1, 1 over 2, 1 over 3, and so. If we sum these terms, 1, 1 over 2, 1 over 3, 1 over k, then we call this sum a series. Okay, and by using this symbol, we write here 1 over k. This is an example of series. Some important points. We call AK is the general term. Similar in sequences, the general term. General term is quite important for series, for calculations of series, and this general term sometimes says as this series has not an infinite sum or finite sum. From this perspective, the general term is important. And for this series, the general term is 1 over k. There is another point which is quite important for a series, and which implies sometimes as this series convergent or divergent. Let me give this important notion. Okay, partial sum. Yes, partial sum. Let me explain this. Let AK is a series consisting of a1 plus a2, a, say, n, and so. Then be a series, then the sequence Sn a1 plus a2 and an is called the partial sum of given series. Okay, the partial sum. And by a partial sum of a series, we will understand a sequence such that its general term consists of the sum of the first n terms. Some explanation. Okay. So our series is this one, k from 1 to infinity, ak, and this is the general term. This is the general term of series. Okay. And the partial sum is a sequence. Let's denote it as Sn. Sn is a sequence such that the general term is the sum of the first n terms. Then the first element, S1, is A1, and the second term, the sum A1 and A2. The third term, A1, A2, and A3. And the general term of this sequence, which is the partial sum of the given series, A1, A2, and an. Okay, then we may write Sn as A1 plus A2, A1 plus A3, A1, an, and so. Okay. So, and from mathematical perspective, this will be not correct, but to make clear, we may imagine the term at infinity order as infinity. As infinity is A1, A2, an, and so. So the last term, we can say that last term. The last term is this sum, which is already given this series. So then we may say that if this sequence is convergent, then this series is convergent. By the way, we say AK is convergent if this sum is a real number. If this sum is equal to infinity, then we call this infinity divergent. Convergent and divergent. Okay. This is the convergent case. And this one, okay, divergent case. So let me remove this part. This is not correct from mathematical perspective, but maybe help of us to make clear. Okay. This is the partial sum. Yes. So we may introduce a series is called convergent, respectively divergent, if its partial sum is convergent, respectively divergent. Okay. Just a notation. Okay, convergent series show this inequality, and the divergent ones like that. Okay, some examples. Find the sum of this series. The general term is 1 over k plus 1. We can write this example and in that way. I mean, observe the character of this series. Those are equivalent. I mean, uh, find the sum of this series, or we can ask observe the character of this series. Those are the same solution. Okay. And first let me say that the general term of this series 1 over k plus 1. Okay, good. And let's show Sn the partial sum of this sequence. Then we may write here n plus 1. Okay, this is a sequence which is the partial sum of this series. So in order to find the sum of this series, we have to find the infinite limit of this series, of this sequence. Sorry. So from the first semester of this course, you know how to separate these fractional statements. I mean, this one, and we may write here a over n, b over n plus 1, and we may write here 1 equals to a plus b n plus a. So this is a polynomial equation. Then the coefficients must be equal. I mean, here should be 0 and this one 1. That's why you can write here 1 over n minus 1 over n plus 1. Okay. Then 1, 2, okay, 2 multiply 3 and n plus 1 equals to, okay, by considering this equality, we may write here 1 minus 1 over 2 plus 1 over 2 minus 1 over 3, 1 over 3 minus 1 over 4. For the term n minus 1, n minus 1 minus n, 1 over n minus 1 over n plus 1. Okay, so this is the first term, and this is the second term, and this is the last term. This is the last term, and indeed we may separate by using parentheses. Yes. Like that. Yes. So, and this equals to by the way, you may see that these terms all remote and equals to 1 over n minus 1. This means that our partial sum is a sequence whose the general term 1 minus 1 over n plus 1. Okay. If this sequences is convergence, then our series is convergence. Otherwise, it will be divergent. Okay. Let's look the infinite limit of the sequences. Okay, and this is the constant term, and so its limit already itself, and 1 over n plus 1, its infinite limit should be 0, and here it should be 0. Just a moment. Okay, here should be 0, then this limit equals to 1. If the limit of partial sum is equal to 1, then we can write here k 1 over infinity from 1 to infinity, 1 over k plus 1 equals to 1. Via this example, we may write a remark here. Okay, given a series AK and its partial sum is denoted by Sn, then k from 1 to infinity AK equals to, yes, you may write this one. Now I'm going to teach as a subsection geometric series and which is very simple. Okay, for a real number a, 1 a plus equals to from 0 to infinity a power k. Okay, it's called a geometric series. Yes. And until now, we have started sequences and series from the first term as indices k1 or n1 anyway. But for geometric series, we start those series and from the k0, but it doesn't matter. You can write here exactly. You can write here k equals to 1 from 1 to infinity a power k minus 1. So it means that it's not a big deal. It's not a big deal. Okay, but the point is, for a geometric series, the first term should be 1, and this is the point. And the other terms, some powers of real numbers. Okay. How to calculate? And infinite geometric series. A geometric series okay, and let's have a look the partial sum of a geometric series. Sn partial sum 1 a square an. We already know this sum is equals to 1 minus an plus 1 over a. Okay. We already know this. Then the geometric this geometric series aj equals to limit and goes to infinity over 1 minus a. Then this limit may be a real number, if the absolute value of a is smaller than 1. Just a moment. Okay, this series convergent in this case, otherwise divergent. Okay, so yeah, we can explain this this limit, you know, in in this statement, n is our variable, and if n goes to infinity, then this those term is constant, and this one also constant. So we have to pay attention this one, and a over n plus 1. We know very well from the first semester, limits as x goes to infinity, ax equals to let's pay x equals to infinity if absolute value of p greater than or equal 1, or 0 if this satisfies. And by using these properties, we can say this equality. And okay, and if a the absolute value of a is smaller than 1, then this number, this is a real number, must be 1 over 1 minus a, because in this case this term should be 0. Okay, then so for a geometrical series, okay, equals to 1 over 1 minus a if a belongs to this interval. Otherwise, this sum is equal to infinity. Okay. Some examples. Okay, some examples. For a geometrical series, its general term says a lot of things, as in this equality. So here a belongs to this interval. The absolute value of a smaller than 1, then this geometrical series is convergent. Then this equals to 1 over 1 minus 1 over 3, and should be 3 over 2. And this one, and This one is a series like 2 over 3, 2 over 3 square, 2 over 3, and so. And we may write here 1 over 2 over 3, sorry, 1 plus 2 over 3, and minus 1, this one. And this one is a geometrical series, which may be written as 0, infinity, okay, k. In this series, a 2 over 3, which means that this is a convergent. So, and this sum equals to 1 over 1 minus 2 over 3, and this should be 3. Okay, good, very good. Here is 3, and this one equals to, I mean this one, let's write here 2. Okay, this is the some easiest examples. Let's continue to examples. One, 2, and 3. From 1 to infinity, minus 1k over square root 5k. Let's observe this infinite series. Okay. And for this series, a is minus 1 over square root 5. But this is not a geometrical series because the first term is it isn't 1. And explicitly we may write this series like that. As in previous example. So one minus 1 square root and its square and minus 1 and minus 1 and so. And now here is a geometrical series, and whose the general term is proper for convergence. That is why here 1 over 1 minus square root 5, and because a is minus 1 over square root, this is belongs to this interval. So that is why this series is convergent. And we may write here square root over square root plus 1. Okay. Then minus 1 over square root multiply square root 5 plus 1 is equals to minus 1. This is an irrational number, so denominator is irrational. We may use conjugate minus or 1 minus square root over 4. This means that this is this okay, 1 minus square root 5 over 4. This wasn't at the beginning a geometrical series, but after some small manipulation, and we have seen it as a geometrical series, and then after some calculations we found this number, and this means that this geometrical series is convergent. And another example that I will not solve, this is for you. Find just a moment. Okay, this is for you. For geometrical series, there are some canonical examples. For instance, okay, just a moment. Anyway, let me draw a rectangle. Okay, in this figure there are some rectangles whose just a moment. Okay. There are some rectangles whose each is drawn by the mean points okay, and find the circumferences of all rectangles. Okay, by the way, the biggest one is 6 and 6. Okay, we can write centimeter, and here is the just a moment, here is the mean points. This means that we may write here 3 and here should be 3 square root 2, and here is the mean point. This one should be over 2. Okay, then the third one should be 3, and so let's write here, find circumferences of all rectangles. Okay, the first one, the biggest one, 4 times 6 centimeters. The second one, 4 times 3 square root 2. Let's write here 1 over square root 2. Third, the third one is 3. This one is 3, and let's write here and multiply 1 over square root square, and so. Okay, we found the geometrical series indeed, and we are looking for this sum. That's why if we write this sum like that, 24 multiply 1 plus 1 over square root 2, 1 over square root square, and so this is a geometrical series, and this is which is convergent, and this one 1 over 1 minus 1 over square root. So we may write here 24 square root 2 minus 1, and this one 24 plus or 48 just a moment. Oh, this is not correct. Just a moment. Okay, this is the result. I mean this 24 multiplied 2 plus square root 2 is the sum of all circumstances of rectangles. Those are the canonical examples for geometrical series. Okay. At the moment, we may finish this part. Okay. So that is an important theorem. I want to show to you. There is a theorem which is very important. The infinite limit of general term of a convergent series is 0. Okay. Some explanation. Okay. If you have a convergent series, then its limit, infinite limit, must be 0. We have already, for example, we have already a convergent series. Yes, this one, and we found this sum. We found this one. Sorry. Yes. We already calculated this series as 1. It means that it is a convergent series. Okay. And our theorem says that if it is convergent, then its general term, the infinite limit of this, its general term must be 0. Yes, that's right here. And one over k plus 1. This is convergent. And its general term 1 over k square plus k is obviously 0. as k goes to infinity. Okay, and equivalently, this theorem, okay, equivalently, if by the way, if you have a proposition, if PQ, then which is equivalent to, okay, this one. I mean, if you have the infinite limit of general term of a convergent series is 0, then you can say that if the infinite limit of the general term of a series is not zero, then this series divergent. Okay, equivalently. I mean, this proposition equals to this theorem. Those are equivalent. Yes, equivalently theorem. Good. By the way, there is a remark which is very important. Let AK be a series if limit as k goes to infinity, AK is 0, then it does not mean the series is convergent, which is very important. Okay, its converse is correct. If your series is convergent, then this limit must be 0. But if this limit is 0, then it doesn't mean the series is convergent, which is very important. Some counter example. Let's take this series 1 over k. So and observe this. Just a moment. Okay, 1 over 2, 1 over 3, 1 over n, and so. Okay, let's look this series. We can write here 1 and just a moment, 1 over 2 and separate 1 over 3, 1 over 4, and separate 1 over 5, 1 over 8, separate 1 over 9, 1 over 16, and so. Okay, and this one clearly bigger than 1 over 2, and this one clearly, because if this is if this would be 1 over 4, this sum equals to 1 over 2. Now must be greater than 1 over 2. And similarly, greater than 1 over 2. And similarly, greater than 1 over 2. So there are infinitely many terms which are greater than 1 over 2. It means that this sum must be infinity. Okay, this series divergent. We obtained its divergent, but the general term obviously the infinite limit of the general term obviously is 0. So that is what I am trying to say. If you have a series which is convergent, then this must be 0. But if the infinite limit of the general term of series is 0, then it doesn't mean the series is convergent. Okay. And now just a moment. A new subsection, series whose all terms are positive, that I will explain in the next video.